Okay, so we have 3 points, and on the previous page we talked about how as long as we have 3 points we can figure out the equation of a plane. So I'm going to try to connect the theory or the abstract idea to our equations here. So again, we have our 3 space. Okay. And we have 3 points that are going to be on the same plane here. So let's draw our parallelogram. So this is our parallelogram, or our plane in space. And let's say we just have point A to be here roughly, point B, and point C. Okay? Those are our 3 points in space right now. Now, like we talked about, we're going to need some directional vectors involved with them. So what we're going to do is we're going to connect these points. And we're going to use one of them to represent the origin. And what we mean by that is, let's say if we were to call A the origin, that means both of the vectors are going to come from there. Now normally the origin is our 0, 0, 0 in 3 space. But we're going to use that to figure out how the direction of AB and the direction of AC are relative to the origin. So we're using one point to start. So we're going to call that our point A. And what we're going to look for is vector AB and vector AC. Once we have directions from A, those directional vectors can be the vectors we put on the origin. So the first thing we're going to do is we're going to solve for vector AB. Okay. And we're also going to solve for eventually vector AC and find directional vectors from them. Okay. So you'll see in the end what's going to happen is our AB could become our new directional vector. We'll call it just vector A. And our AC can become our new directional vector. We'll call it B from the origin. From there, we'll be able to essentially calculate our equation of a plane. So, how can we calculate AB? Anyone know? Yeah, point B minus A. Okay, so in other words, we're also looking at our x2 minus x1, y2 minus y1, and z2 minus z1. This is equivalent of point B minus point A. Okay? Could call them vectors, but we'll leave it for now. So, if this is our second point and this is our first point, that means we're looking at -1, subtract -1. 1 subtract 3, and 0 subtract 8. This is going to give us 0, -2, -8 as a directional vector for AB. Is that right? That what they found? 0, -2, 8. Great. AC, same idea. We're just going to call this point 2. We won't rewrite the equation though. This will become 4 subtract -1 again, 1 subtract 3, and 1 subtract 8. So directional vector for AC is going to be 5, -2, -7. Okay? So we now have 2 directional vectors. These 2 directional vectors are going to help us. Did I do that right? Yeah. So we have our 2 directional vectors. 9. Hold on. Okay. Sorry. We just used different directional vectors than what they had, but that's fine. So we've calculated vector AB, or in this case, like we said, our vector A, or our directional vector A, and what we've called directional vector B. So we have our 2 direction vectors. It's fine. You can use any points along this to find them, because a plane is going to have an infinite number of lines along it that can use to determine the plane. And we just need a 3rd point along it for our equation. If you remember, our vectored form of our equation was our vector r, or plane r, is r naught plus s directional vector A plus t directional vector B. So we can call this our directional vector A and directional vector B. And our r naught just needs to be one of our points. Well, we have 3 points that we can use. Any of them are acceptable. It's completely up to you what you guys want to use for this. So we know that a point on this plane, or r naught, we could call it A, B, or C. We'll call it A since this is alphabetical. It's the first one. -1, 3, and 8 plus, zoom in for this part, a scalar of directional vector 0, -2, and 8, and directional vector 5, -2, and -7. Okay. Now, in the book, they've used something a little different, but they're still on the same plane. They used AB, and then they used another directional vector, BC. It's fine, because these two vectors, or the directional vectors, will still end up representing the exact same plane, because the plane is infinite in size. Okay? And any scalar multiple of those two directional vectors will still make the exact same plane. These vectors end up being on the same plane, and the very important part is our point on the plane. So that to prove it's not technically on our XY or YZ axis, this point lets us know that this is a plane in 3 space. Okay, B gives us actually 2 points, and they ask us if they lie on this plane. So what we're going to do is we're going to take our equation. I'm just going to jump to another page here. Exactly. So we're in vector form right now. Okay. What we're going to do is we're going to change it to parametric form in order to solve for the 2 points that they've given us. And I guess I should write those down. They've asked us if point P, 14, 1, and 3, lies on it, and if point Q, 14, 1, and 5, lies on this plane. So, parametric form, if you remember, we're going to have our x, our y, and our z. That's all that vector r stands for. This is some point on this plane. And the plane is defined by the 2 directional vectors 0, -2, 8, and 5, -2, -7. Now, technically, our directional vector, specifically this one here, I can factor a number out and make it a simpler number to use. Okay. This could also be known as directional vector 0, -1, and 4, where I factored the number 2 out of this. Either will work, because one's just a scalar multiple of the other. Okay. Our other directional vector, we don't have a whole number that we can take out. Obviously, we can take out fractions, but probably going to make our calculations a little more complex. But let's focus on the task. We're going to turn this into parametric form, which means our x is going to be a multiple of 1, 0s, and 5t. Y is going to be a multiple, or an equation that has our 3, -2 in s, -2 in t, and z is going to have our 8, 8s, -7t. Okay? So we're going to write out these 3 equations here. We have x is equal to -1 plus 0s plus 5t. X is equal to -1 plus 5t. Y is equal to 3 minus 2s minus 2t. And our z is equal to 8 plus 8s minus 7t. Okay. Now, they've given us points or coordinates that are considered an x, a y, and a z. So, what we can do here is we have our 3 equations. Here's our equation 1, equation 2, and equation 3. We have 3 equations. We also have 3 numbers that we're going to plug in. We're going to plug these numbers in for our x, our y, and our z. And then we're going to see if s and t are equal throughout all 3 equations. If they're equal throughout all 3 equations, then we know we have a point on the plane. If they are not equal throughout the three equations, then we're looking at a point that's not going to be equal on this plane. So let's plug these in. Our first equation 1, x, we're going to use the number 14 to represent it. So equation 1, 14 is equal to negative 1 plus 5t. Because there's no s in this equation, this works out great. We could solve for t right away and plug it into the other two. In this case, we're going to get 15 is equal to 5t, t is equal to 3. Okay. So, since we already have a variable for t, let's plug it into equation 2. Equation 2, y, whoops. We have a value for y. Our y is the number 1, in this case, is equal to 3 minus 2s minus 2, and our t is the number 3. We'll try to isolate 4s. We bring, this is 6, we bring it to the other side, becomes plus 6 minus 3 equals negative 2s. Okay. 7 minus 3 is 4 equals negative 2s. S is negative 2. Okay.
Hello?
Yes.
Hi, has Roger been in class?
So we now have values for t and s. Once we have these two values of t and s, we plug them into equation 3. And let's see if they hold true. We know it holds true for equation 2. We should technically test equation 1. Oh, sorry. Equation 1 doesn't have a variable. So equation 1 and 2, we've held true. Test out equation 3 with these two variables. So 3 said that z, which had a coordinate of the number 3, was equal to the number 8 plus our s is negative 2, so 8 times negative 2, minus 7 times 3, which is our t. So we're going to calculate 3 is equal to 8 minus 16 minus 21. 3 equals 8 minus 16 is negative 8. Minus 21. 3 is equal to negative 29. These are definitely not equal. So we're not looking at a point that is on our plane right now.